Did anyone ever tell you the universe began with the Big Bang, an unimaginably huge explosion that gave birth to time, space, and everything we know? But what if that story isn't the complete picture? What if the Big Bang was not the true cosmic starting point, but merely the consequence of something far stranger? Some scientists propose that we don't just live in a universe, but that we are trapped inside the belly of a cosmic beast, a massive, unimaginable black hole, which swallowed a higher dimensional world and then spat out our universe. If this is true, what does it mean for who we are and what reality is? If we are truly inside a black hole, is everything we thought we knew about reality fundamentally wrong? Tonight on the Cosmic Series, from the Big Bang to the holographic universe, we will follow physicists step by step to deduce how reality would be rewritten if we truly reside inside a black hole. Black holes are among the most bizarre objects in the universe. They are invisible regions of space where gravity is so extreme that they don't just challenge our curiosity, but directly challenge our understanding of reality itself. The journey of black holes, from a far-fetched conceptual idea to an indispensable fixture in modern cosmology, is itself a scientific thriller full of reversals. What draws us in is not just their gravitational pull on stars and planets, but their profound impact on human imagination and our cosmic worldview. The concept of a body so dense that not even light could escape its gravity can be traced back to the 18th century musings of the English clergyman and scientist John Michell. He didn't call them black holes, and he had no way to prove the idea at the time, but his foresight planted the seed for later scientists. At the time, these ideas were more akin to thought experiments than actual physical theories, and they were largely buried for nearly 2 centuries before returning to the stage as rigorous science. Fast forward to the early 20th century, when Albert Einstein introduced his general theory of relativity, fundamentally changing humanity's view of gravity. Before this, gravity was seen as a force between objects, like the Earth pulling on the Moon. Einstein stated that gravity is not a force in the traditional sense, but the effect of mass warping spacetime. Massive objects, such as stars, cause the surrounding spacetime to curve like a depressed rubber sheet, and less massive objects simply follow the path of this curvature. This conceptual shift opened the door to the existence of extreme objects like black holes. Interestingly, Einstein himself disliked the implication of black holes and found it hard to believe that nature would allow such extreme structures to actually exist. But mathematics does not yield to personal preference. In 1916, German physicist Karl Schwarzschild, while serving on the front lines of World War I, derived a specific solution to Einstein's equations. He found that under certain conditions, a sufficiently massive star would collapse under its own gravity to an infinitely dense point, forming a gravitational abyss, what we now call a black hole. Schwarzschild's finding was momentous, but his work was initially lost in the chaos of World War I. Nonetheless, his calculations provided scientists with a completely new cosmic possibility. Schwarzschild's solution not only predicted the existence of black holes but also described their boundary, later named the event horizon. This is the point of no return. Once crossed, not even light can escape. Even with Schwarzschild's solution, black holes were considered mathematical monsters for a long time, and many scientists doubted their physical existence in the real universe. Einstein himself repeatedly warned against overinterpretation, believing that conclusions pushing his equations to black holes were a gross misunderstanding of general relativity. The situation only changed decades later when astronomers began to discover strange objects in the cosmos. In the 1960s, a binary star system called Cygnus X1 was identified, where one star appeared to be orbiting something invisible. Scientists later confirmed this invisible companion was extremely massive but non-luminous, perfectly matching the characteristics of a black hole, making it the first widely accepted candidate system. The truly fascinating aspect of black holes is their radical disruption of space-time. Near a black hole, time slows down. This is not science fiction, but a direct consequence of general relativity, confirmed by similar observations in strong gravitational fields. If you could hover near a black hole and look back at Earth, you would observe that time on Earth seems to be speeding up. This means the flow of time can be drastically different in various locations within the same universe. This warping of time and space is not just a theoretical detail, it is one reason why some scientists believe black holes hold one of the universe's greatest secrets. Black holes attract not only scientists but also artists and writers. Long before the scientific evidence was conclusive, literary and artistic impressions similar to cosmic black holes had appeared. Influenced by Einstein's theories, surrealist painters like Salvador Dali incorporated impressions of infinitely warped space-time into their works. By the 20th century, the black hole became a symbol of both dread and fascination in popular culture. The term, black hole, itself was formally coined by physicist John Archibald Wheeler only in 1967. Before that, people used simpler terms like dark star or frozen star. The new name quickly caught on, partly because it was catchy, but mostly because it perfectly captured the sense of a mysterious abyss. Later, from the Disney film The Black Hole to the sci-fi film Interstellar, black holes have been continuously used as plot devices, tightly weaving science and imagination. Yet, even though black hole is a household term, the underlying science remains profoundly deep. Contrary to the passive swallowing many imagine, the environment around a real black hole is highly active. As gas and matter spiral into the black hole, they form a ring-like structure called an accretion disk. The material in the disk heats up to millions of degrees due to intense friction and compression, emitting powerful X-rays that astronomers can detect on Earth. Some black holes also eject jets that shoot out at near light speed, highly concentrated streams of energy and particles. These jets can extend for thousands of light years, directly impacting the distribution and evolution of matter within galaxies. It is precisely because of these links between black holes and large-scale cosmic structure that scientists value them so highly. At the center of our Milky Way galaxy, there lies a supermassive black hole called Sagittarius A*. Such black holes can have masses millions or even billions of times that of the Sun, yet their volume may not be much larger than a planetary orbit. Their gravity acts like a cosmic anchor, tightly binding entire galaxies together. Without these cosmic anchors, it is questionable whether galaxies, and thus the familiar forms of life, could exist. The core significance of black holes is that scientifically, they push us to the edge of human knowledge. At the very center of a black hole, theory suggests there must be a point of infinite density, the singularity. Here, almost all existing laws of physics break down, and concepts we take for granted, like space and time, lose their meaning. Many physicists believe that if we can truly understand the singularity, we might understand how the universe was truly born. One perspective even suggests that the Big Bang itself may have been the outburst of some kind of cosmic singularity, marking the moment our universe ignited from an extremely dense state. Black holes' connection to other cosmic phenomena is tighter than we imagine. One of the brightest objects in the universe, the quasar, is powered by a supermassive black hole. As vast amounts of matter plunge into these black holes, energy brighter than an entire galaxy is released. It is through the study of quasars that scientists have further understood how black holes devour matter yet unleash light. This paradoxical characteristic, being both a destroyer and a massive energy generator, is a key reason why they continue to attract public and research attention. Modern observation tools have allowed us to see a black hole for the first time. In 2019, the Event Horizon Telescope Collaboration, a network of radio telescopes around the globe, released the first image of a black hole in human history. It showed the shadow of the supermassive black hole at the center of the M87 galaxy, surrounded by the bright glow of its accretion disk. This was not just a scientific milestone but a cultural moment. Humanity had seen the dark abyss born from equations with its own eyes. This image confirmed many key predictions of general relativity and raised new questions. What is hidden just inside the bright inner ring? Could those invisible regions contain clues about higher dimensional space or hidden dimensions? Some theories propose that our entire universe may have been born inside a black hole in a higher dimensional space. These black holes act as cosmic factories, collapsing in higher dimensional space-time and then giving birth to new three-dimensional universes within. Such ideas resonate with the so-called holographic principle, where all our experience in the three-dimensional world may be merely the projection of information contained on a two-dimensional boundary surface. From this perspective, black holes are no longer just cosmic oddities, but a gateway to understanding the nature of reality. This connection becomes even more pronounced in the study of gravitational waves, which are ripples in space-time. Since their first direct detection in 2015, many of these waves have been found to be generated by merging black holes. By listening to these deep space oscillations, scientists are getting to know black holes with a completely new sense. Every detection provides more evidence of a complex and profound coupling between black holes and the overall structure of the cosmos. Although we are far from having all the answers, it is certain that black holes are far more than just extremely strong gravitational regions. They play a vital role, from the birth of galaxies to the possible ultimate fate of the universe. Regardless of whether future discoveries confirm that black holes truly lead to other universes, or whether they ultimately only show us the limits of human knowledge, black holes will remain one of the most mysterious, awe-inspiring, and fascinating objects in the cosmos. Einstein's general theory of relativity fundamentally changed how we understand space, time, and gravity. Before its arrival, we viewed gravity as a mutual attraction between two objects, but general relativity told us that gravity is actually the curvature of spacetime itself. Any object with mass deforms the surrounding spacetime, and other objects simply follow the path of this curved spacetime. A common analogy is stretching a rubber sheet flat, placing a heavy ball on it, causing the sheet to dip, and a smaller ball placed nearby will roll toward the larger ball. This is the geometric interpretation of gravity. General relativity is not just an elegant mathematical theory, it successfully explained many astronomical observations. One of its most astonishing predictions was the existence of the black hole. When Einstein published his field equations in 1915, he himself could hardly believe that nature would allow such an extreme object to truly exist, a place where gravity is so strong that even light cannot escape. It sounded more like science fiction than a cosmic fact. However, mathematics leaves no room for sentiment. In the midst of the battlefield, Schwarzschild derived an exact solution to Einstein's equations, describing an idealized, static, and spherically symmetric gravitational field. If a star is massive enough and exhausts its fuel, it cannot resist its own gravity and collapses. In the Schwarzschild solution, this collapse compresses the matter into an extremely small region, forming the so-called singularity. Outside the singularity appears a crucial boundary, the event horizon. The event horizon is not a physical surface, but an invisible mathematical boundary. At this boundary, the escape velocity, the minimum speed required to break free from the gravitational pull, exceeds the speed of light. Since nothing in relativity can travel faster than light, once this horizon is crossed, no particle, not even light itself, can ever return. To an external observer, an object falling into the black hole appears to slow down and dim as it approaches the edge of the horizon, seemingly stopping there forever. However, to the object itself, it continues its inward plunge in a finite amount of its own time, heading towards the inevitable singularity. Inside the event horizon, the curvature of spacetime reaches an extreme. Conventional laws of physics largely break down. At the central singularity, density and spacetime curvature theoretically tend towards infinity, which is where current theories encounter insurmountable difficulties. Some physicists believe that the singularity might not be a physical reality, but rather a warning that general relativity is overextended under such extreme conditions, necessitating a new theory of quantum gravity to take over. Black holes do not come in only one size. The most common type is the stellar mass black hole, formed by the collapse of massive stars at the end of their lives, typically a few to a few dozen times the mass of the Sun. Far larger are the supermassive black holes, which can be millions or even billions of times the solar mass, generally located at the centers of galaxies. Our Milky Way core harbors one such black hole, Sagittarius A*. Falling between these are intermediate mass black holes, spanning from hundreds to tens of thousands of solar masses, possibly formed by the merging of multiple smaller black holes. Their existence is still actively being confirmed with definitive examples. There is also the highly speculative primordial black hole, which, if they exist, might have formed from density fluctuations in the very early universe and could be extremely tiny. They may also be related to the mystery of dark matter. The personality of a black hole is also related to its rotation and charge. If a black hole retains angular momentum during its formation, it will rotate. This spinning black hole is described by the Kerr solution. Rotation drags the surrounding spacetime with it, an effect called frame dragging or the lens-thirring effect. Under this effect, space itself is twisted like a vortex, and any object or light ray near the black hole is swept up in this rotation. The Gravity Probe B experiment precisely measured a much smaller version of this effect near Earth. Theoretically, there can also be charged black holes Reissner-Nordstrom solution, but since most objects in the real universe are electrically neutral overall, large charged black holes are considered unlikely to be common. Although the interior of a black hole seems inescapable, it does not mean their exterior is entirely cold and dark. On the contrary, the region around a black hole is often one of the most violent and hottest in the entire universe. When gas, dust, or even entire stars are captured by the black hole's gravity, they form an accretion disk. The matter in the disk spirals inward while orbiting the black hole, heating up to millions or even hundreds of millions of degrees under intense compression and friction, emitting powerful X-rays and gamma rays. This high-energy radiation travels through interstellar space and is captured by ground or space telescopes, serving as our indirect evidence of black hole activity. Some black holes, especially the supermassive ones at galactic centers, also release gigantic jets. These jets are streams of high-energy particles and magnetic fields ejected from the poles, aligned with the black hole's rotation axis, traveling at near light speed into interstellar space. These jets can extend for thousands or even tens of thousands of light years, profoundly influencing the distribution of surrounding interstellar gas and the formation history of entire galaxies. Time also behaves strangely near a black hole. According to general relativity, the closer you get to a strong gravitational field, the slower time passes. This is called gravitational time dilation. On Earth, precision atomic clock experiments have confirmed that time at the top of a mountain moves slightly faster than at sea level. Near a black hole, this difference is amplified to the extreme. If you were safely floating slightly away from a black hole and watched a person fall in, you would see their movements slow down and their light redshift, as if they never quite reached the event horizon. Yet, from their own perspective, the fall is finite and irreversible. By studying black holes, scientists have not only learned how to describe extreme gravity but have also used them to understand many other cosmic phenomena. For example, quasars are driven by the violent accretion near supermassive black holes, with brightness exceeding that of entire galaxies. This tells us that while black holes project an image of all-consuming darkness, they can, through complex physical processes, transform infalling matter into astonishing light and energy. Black hole research is also linked to the overall fate of the universe. Through gravitational wave observations, we have directly witnessed the spacetime ripples generated by the merger of black holes. For instance, in 2015, the LIGO team first detected the gravitational wave signal from the collision of two stellar mass black holes. This not only verified Einstein's prediction but also showed us that black holes play a vital role in cosmic evolution, constantly meeting, colliding, and merging, reshaping the structure of spacetime. Hawking's proposal of Hawking radiation further complicated the black hole picture. Quantum theory suggests that the vacuum is never absolutely empty, but is constantly producing and annihilating virtual particles instantaneously. Near the event horizon, this process can be interrupted by gravity, with one particle falling into the black hole and the other escaping. From a distance, this looks as if the black hole is slowly evaporating. Although Hawking radiation has not yet been directly observed, it has profound implications for black hole lifetime, information conservation, and the theory of quantum gravity. In summary, Black holes are no longer mere mathematical monsters or sci-fi tropes but are indispensable protagonists in contemporary physics. By studying them, we are simultaneously testing general relativity, quantum theory, cosmology, and high-energy physics, constantly pressing against the question of how space, time, matter, and information behave under extreme conditions. String theory introduces the stunning idea that the universe may consist of more than just our familiar three spatial dimensions plus one time dimension. In some versions of string theory and M-theory, the total number of dimensions can reach 10 or even 11. These extra dimensions are thought to be compactified, or curled up to an unimaginably small scale, like a tightly rolled up paper edge, making them virtually unnoticeable in our daily lives. They are not intuitive like length, width, and height, yet they play an indispensable mathematical role. Without them, the equations struggle to accommodate all fundamental interactions simultaneously. Within such a higher dimensional framework, the idea of the universe being born inside a black hole becomes less outlandish. A model known as the Brin world suggests that our universe is simply a three-dimensional membrane, or Brin, floating within a larger, higher dimensional space called the bulk. We can imagine it as a thin sheet floating in an ocean, where other membrane universes may also exist in the same sea. The reason gravity appears particularly weak in our universe may be that some of its lines of force leak into the higher dimensional bulk space, so we only perceive a fraction of it. In this perspective, black holes might be far more complex objects in the higher dimensional space. To our 3D perspective, a black hole is a dense object with an event horizon, but if viewed from a higher dimension, their shape and properties could be entirely different. Some theories even propose the existence of black brins, high-dimensional black holes extended along multiple dimensions. When these higher dimensional black holes collapse or interact, they might pinch off a detached region of spacetime. This pinched-off spacetime then expands internally, forming a new universe. This is the intuitive path behind certain black hole cosmology hypotheses. M-theory, a more unified framework developed from string theory, emphasizes 11-dimensional spacetime and the existence of various membrane-like objects. Under M-theory, gravity, electromagnetism, and the strong and weak nuclear forces are all expected to be incorporated into the same mathematical structure. In this unified view, black holes are no longer isolated objects but nodes where multidimensional structures and fundamental interactions converge. Some researchers propose that our universe may be the product of a collapse and rebound process that occurred inside a higher dimensional black hole. The Big Bang, therefore, would not be an absolute beginning but the aftermath of a gigantic higher dimensional change. A core idea of the black hole universe hypothesis is linking the extreme state inside a black hole to the Big Bang in the early universe. Inside a black hole, matter and energy are compressed to extremely high densities, and the spacetime structure is warped to the brink of collapse. Some models propose that when the compression reaches a certain limit, quantum gravity effects prevent a true singularity of infinite density from forming, instead triggering a bounce process. A new spacetime bubble then forms internally and begins its own expanding evolution. From the inside, this is a Big Bang. From the perspective of an external observer, it is merely a process of the black hole forming or growing. But from the perspective of the new internal universe, it is the start of time. In other words, their Big Bang might just be the aftermath of a black hole collapse event within our universe. The event horizon plays the role of a boundary between universes in this hypothesis. In a regular black hole, the event horizon is a line of no return. In the black hole universe model, it can be viewed as the separation surface between the mother universe and the baby universe. We cannot see the edge of our own universe, just as an observer outside a black hole cannot see its internal structure. This might be because all information is encoded on some higher dimensional boundary, which dovetails with the holographic principle. The physical information within a volume of space might be entirely encoded by the two-dimensional surface that encloses it. This gives the holographic principle a deeper meaning. All the 3D reality we experience is a projection of information on a 2D boundary. Black holes act like information hard drives, storing both the information of the matter and energy they swallow and potentially hiding the structural clues of a previous universe. Other theories further connect this to cosmology. The accelerated expansion of the universe, the so-called dark energy effect, might be related to the influence of the external higher dimensional space. If our universe is a bubble within a larger structure, external tension, pressure, or the leakage of gravity could manifest macroscopically as the dark energy we measure. The black hole universe hypothesis is also tightly linked to the second law of thermodynamics, which states that entropy always increases. Black holes themselves possess entropy, and black hole entropy is proportional to the area of the event horizon, not its volume. This suggests a profound relationship between spacetime structure and information storage. If our universe is a spacetime bubble inside a black hole, the total entropy of the universe might also be recorded on a two-dimensional boundary. This provides a new perspective for understanding why the universe has a time arrow and why entropy increases. The behavior of time inside and outside a black hole might also differ. As an object approaches the event horizon, time is infinitely stretched for the external observer, but in the infalling observer's own time coordinate, they cross the horizon in a finite time. Combining this extreme time warp with cosmic expansion, some propose that the accelerated expansion we observe internally might be a projection of some time flow difference from a higher dimensional perspective. These ideas are undoubtedly bold, and many remain in the stages of theoretical and mathematical deduction, but they construct a highly imaginative perspective. Black holes are no longer just the endpoints in the universe but nodes and seeds connecting different universes and different dimensions. In such a multi-layered structure, the Big Bang is no longer a solitary, unique beginning but potentially a common opening act in a cyclical sequence of black hole universes. Imagine a scenario. In one universe, you choose to turn right at a crossroads, while in another, you turn left. In one timeline, you decide to grab lunch, in another, you stay hungry and keep working. If all these minute divergences evolve into complete worlds, the multiverse is formed. While this sounds like science fiction, the concept of parallel worlds actually originated in quantum physics, which tells us that microscopic particles can exist in multiple states simultaneously, and we only force them to choose when we measure them. Some researchers have scaled this superposition of multiple possibilities to the entire cosmos, proposing a model where every possibility is realized in some universe, a concept sometimes visualized as an infinite foam of separate, bubble universes. As each new universe bubbles into existence, it may possess its own unique physical laws and constants, isolated from the other bubbles. However, some theories suggest that these bubbles may not be entirely isolated, and black holes could serve as the connection points between them. One view suggests that black holes can link different universes. When matter falls into a black hole in one universe, the extreme gravitational field might tunnel a pathway through the higher dimensional spacetime. Energy, matter, or even some form of information could potentially pass through this conduit into another universe. In this picture, black holes are no longer just endpoints but cosmic checkpoints and transfer stations between universes. Another type of multiverse scenario arises from brane theory, where our universe is a three-dimensional brane floating in a larger, higher-dimensional bulk space. You can imagine it as a piece of paper floating in a larger space, with other universes being nearby sheets of paper. In this brane model, black holes can form on the various branes, and their intense gravitational fields might pull connections between different branes in the higher dimensions, allowing energy or gravity to leak between the universes. Some argue that gravity appears especially weak in our universe precisely because it is constantly leaking into other brane universes. Speaking of pathways, the most imaginative concept is, of course, the wormhole. Wormholes are often depicted as shortcuts connecting two distant points in space-time. Taking this a step further, one can imagine a wormhole that connects not just two places within the same universe, but two entirely different universes. Some theories propose that a black hole and its inverse, a white hole, might be connected through a wormhole. The black hole end only allows matter to enter, while the white hole end only allows it to exit. Matter that falls into a black hole in our universe might, in some form, erupt from a white hole in another universe. However, to keep a wormhole stable, theory requires the support of exotic matter with negative energy, a substance that has not been directly observed in our everyday world, though it is mathematically permissible. Scholars speculate that the immense energy and warped spacetime of rotating black holes might provide the energy source to sustain wormholes, allowing certain wormholes to briefly open under extreme conditions. On a more microscopic level, there is the idea of spacetime foam, where spacetime itself fluctuates at the quantum scale. Some theories suggest that the interior of black holes or the region near the event horizon might be riddled with tiny quantum wormholes. These wormholes form an invisible network connecting different regions or even different universes. While they are impossible to traverse macroscopically, they might quietly operate on an informational level. If black holes can indeed connect different universes, the question of the universe's boundary becomes subtle. In the traditional approach, we view the universe as a single entity, either bounded or unbounded. But in the multiverse plus black hole gateway scenario, each universe is like a puzzle piece, and black holes are the joints between them. The end of this universe might not be an empty void, but the entrance to another piece of the puzzle. This also casts black holes in the role of cosmic recyclers. Matter and energy shredded by a black hole in one universe might be reassembled in a brand new form in another. From that side's perspective, this is simply the initial matter raining down from the heavens, while from our side, we only see them vanish across the event horizon. Multiverse theories are also subtly linked to certain observational puzzles. For example, could the ripples left in spacetime by merging black holes, the gravitational waves, carry subtle hints from other universes? When scientists spot unusual, hard-to-explain patches in the cosmic microwave background radiation, the afterglow of the Big Bang, some speculate that these might be traces of an early universe contact with other universes. Also, the extremely intense gamma-ray bursts from distant galaxies have led some to wonder if they are related to high-energy events in other universes. Of course, none of these are close to confirmed. They are currently more like scientifically informed speculative inspiration. But together, they paint a bold possibility. Black holes may not be cold gravitational traps, but nodes in the multiverse network, where every black hole could be a gateway to another reality. To truly understand the behavior of black holes, a verbal description is insufficient, we need mathematics. Einstein's field equations sound abstract, but they are the foundation of our black hole research. These equations are a set of coupled, nonlinear differential equations that essentially tell us how spacetime curves wherever mass and energy are present. Initially, solutions could only be found for highly idealized situations, such as the stationary, non-rotating, perfectly spherical black hole. Schwarzschild provided the solution for this simplest type of black hole. It defined the location of the event horizon and described the trajectories of light and matter approaching the black hole. Real black holes, however, are far more complex than this ideal model. Most black holes rotate, some very rapidly. The solution describing a rotating black hole is the Kerr solution. In this solution, the spacetime surrounding the black hole is twisted into a colossal vortex, with even light rays being swept along. Mathematically, the Kerr solution is far more complex than the Schwarzschild solution, requiring numerical methods on computers. This is the world of numerical relativity. Simply put, it involves using supercomputers to simulate Einstein's equations. Spacetime is divided into a grid of points, and at each point, the gravity field's change is calculated. Then time is advanced in small steps, piecing together an animation of the black hole's evolution. The most common method is called finite differencing, which breaks the continuous differential equations into many discrete steps, updating the spacetime curvature at each grid point in every step. To calculate key regions with greater precision, adaptive mesh refinement is used, which automatically refines the grid near the event horizon, black hole merger zones, and other critical areas, while using a coarser grid further away to save computational power. Simulating the mutual orbiting and final merger of two black holes is even more challenging. Two immense gravitational sources pull and twist spacetime, constantly releasing gravitational waves, like ripples spreading on a water surface. The computer must simultaneously track the positions, shapes, and event horizon changes of both black holes, as well as the surrounding spacetime fluctuations. When they finally merge into a new black hole, spacetime enters a ring-down phase, vibrating like a struck bell before slowly settling down. The gravitational waves emitted during this process are characterized by specific frequencies called quasi-normal modes. The results of these simulations align remarkably well with real observations from gravitational wave detectors like LIGO. In 2015, when humanity first directly detected the gravitational wave signal from a black hole merger, scientists compared the data with pre-run numerical simulation templates and found the waveforms matched almost perfectly. This suggests that our mathematical description of black hole dynamics is highly reliable, at least in this domain. To perform such simulations requires astonishing computing power. Supercomputers like Blue Waters or Summit can perform billions or more operations per second, and a complex black hole merger simulation often takes days or longer to run. Researchers distribute the massive computational task across hundreds or thousands of processors running in parallel, with each processor handling a portion of the spacetime grid before the results are stitched together. The behavior of light is also a key focus of the simulations. Near a black hole, light does not travel in a straight line but along geodesics, the shortest paths in curved spacetime. Geodesic tracing calculates, step by step, how light rays circle, deflect, or are captured by the black hole. The results show that light can orbit the black hole multiple times before escaping to distant space. These multiple orbits stack up to form the photon ring, which is the bright ring we saw in the famous M87 galaxy black hole image. The Event Horizon Telescope collaboration used a method called interferometry, virtually synthesizing a globally distributed network of radio telescopes into an Earth-sized telescope, then using complex algorithms to reconstruct the collected signals, finally assembling the image of the black hole shadow and its surrounding photon ring. Excitingly, the structure of these real images highly matches the predictions of numerical simulations. Simulations not only help us understand how light bends but also how accretion disks and jets work. In the computer models, scientists include the infalling gas and magnetic fields into the calculation. The results show that the intense friction within the accretion disk and the mutual collision of particles moving at near light speed, along with powerful shear forces and magnetic field reconnection, heat the matter to millions of degrees, producing high-energy radiation. When the magnetic field lines are twisted into a spiral by the black hole's rotation, they can launch some material outward from the poles, forming the narrow, bright relativistic jets. One of the mathematically trickiest problems is dealing with the singularity. Near the singularity, density and curvature tend toward infinity in the equations, and normal numerical algorithms quickly break down. For this, scientists use the excision method, simply cutting out the tiny region containing the singularity from the computational grid and only evolving the region outside and near the event horizon, because energy and information from the singularity cannot be directly observed anyway. Additionally, choosing an appropriate coordinate system can greatly simplify the calculation. Instead of using a Cartesian grid like a chessboard, adopting coordinate systems that better conform to the black hole's geometry, such as spherical coordinates, can reduce numerical errors in certain directions and stabilize the simulation. Through all these efforts, scientists are gradually building an increasingly concrete picture of black holes. The event horizon is not always perfectly smooth but develops bulges and twists during mergers and perturbations. Rapidly rotating black holes strongly drag the surrounding spacetime, creating complex spacetime vortices. The frequencies and decay patterns of gravitational waves accurately reflect the black hole's mass and spin rate, as if leaving the black hole's sonic signature in spacetime. These mathematical models and simulations tell us that black holes are not static dark spots but highly dynamic, evolving spacetime structures, becoming visible and audible cosmic players through the combined portrait painted by equations and data. Crossing the black hole's event horizon is like stepping through a door where the laws of physics begin to deform. Once you traverse this invisible boundary, you enter a world where all paths point to the center. No matter how you fire your rockets or struggle, the ultimate outcome is only one: approaching the black hole's core. To a bystander observing safely from afar, your approach to the event horizon would appear to slow down indefinitely, and the light you emit would become redshifted to longer, dimmer wavelengths due to gravitational redshift, eventually fading almost completely from their view. In their eyes, you seem to forever stop near the event horizon, never truly crossing it. But for you, time continues normally. You will cross the event horizon in a finite amount of your own time. Once that line is crossed, every possible direction of movement leads to the same outcome: movement toward the black hole's center. A vivid way of putting this is that inside the black hole, the roles of time and space are partially exchanged. Just as in the external world you can only move forward a long time and not back to the past, inside the black hole, you likewise cannot move away from the spatial direction toward the singularity, because that direction has mathematically become your future. During this journey, you would experience what is called spaghettification. Due to the extremely steep change in gravity with distance near the black hole, the end of your body closer to the black hole experiences significantly stronger gravity than the end farther away. The result is that you would be stretched and thinned, pulled apart like a strand of spaghetti. For smaller black holes, this tidal force is strong enough to completely tear apart an object outside the event horizon. You would be pulverized before you even truly fell in. However, the situation is different for supermassive black holes. Because their event horizon radius is much larger than that of stellar mass black holes, the gravitational gradient near the horizon is relatively smaller, and the tidal forces would not instantly dismantle you. Theoretically, you could cross the event horizon largely intact, with tidal forces only becoming strong enough to truly spaghettify you in the region closer to the center. As for the singularity at the heart of the black hole, it is where all our existing physical theories collectively fail. In classical general relativity, the singularity is described as a point where volume tends to zero and density tends to infinity. Space-time curvature also diverges to infinity, and all equations lose meaning. Many physicists believe this does not mean that infinitely large physical quantities truly exist in the universe, but rather serves as a warning that new theories, such as quantum gravity, must be introduced to supersede the old approach. One speculation is the Planck star. In this model, the collapsing matter, upon reaching an extreme density, is held up by quantum gravity effects, prevented from compressing to a true singularity. Instead, it forms an extremely dense but finite core at the Planck scale. From the outside, it still behaves like a normal black hole, but internally, the spacetime structure and the state of matter might be completely different from the classical picture. A bolder idea is that black holes hide baby universes. According to this view, when matter collapses to a critical state, it triggers a Big Bang-like process, giving birth to an independent new universe inside the black hole. From the outside, everything disappears into the black hole. From the perspective of the internal inhabitants, their universe began with a Big Bang, and the mother universe's black hole became the baby universe's singularity. Additionally, some interpretations suggest that wormhole structures might exist inside black holes, connecting the internal region of the black hole to other distant regions in the universe or even other universes. However, Traversable wormholes require many stringent conditions, including the exotic matter mentioned earlier, and remain at the level of theoretical speculation. Another controversial hypothesis is the firewall paradox. It proposes that an extremely high-energy firewall might exist at the event horizon, instantly destroying any matter and information attempting to cross it. This resolves the question of how information is preserved inside the black hole, but it clashes with the principle in general relativity that a freely falling observer should notice nothing unusual at the event horizon, sparking intense debate in the academic community. The situation is even more complex in rotating black holes occur. Theoretically, the singularity of a rotating black hole is no longer a point but a ring-shaped structure. In this internal region, the causal structure of spacetime can be severely warped. Mathematically, it even allows for bizarre paths like closed time-like curves (CTCs) where circling back leads you to your own past. To avoid these counterintuitive results, principles like the cosmic censorship hypothesis have been proposed, which roughly state that nature automatically prevents such naked singularities and causal confusion from appearing in the observable universe. That concludes today's discussion. We hope you have pleasant dreams and a wonderful day. We'll see you next time.